Miners receive transactions from users and pack them into blocks. If you want your transaction to go through, you need to pay a fee for the space it occupies on a block. Here's how this market works. Users bid for block space by attaching fees to their transactions, and the next block producer fills the block to capacity with transactions offering the highest bids. So we're looking at an auction-style market where the higher the demand, the higher the winning bids. What's really interesting about this market is how volatile it can be. If you look at the average Bitcoin transaction fee over time, you'll see big spikes where fees triple in value only to drop down again after a few months. It's much more volatile than traditional markets. Think of commodities like oil or consumer products like light bulbs. Those markets don't see these wild swings, so why do we see them in the blockchain world? Well, it's all about supply and demand, and more precisely, it's about the elasticity of supply. You see, in most markets, when demand increases, suppliers respond by making more of the product. For instance, the demand for ice cream increases every summer, and the supply adjusts in tandem. If this adjustment is quick, we say that supply is highly elastic, because it works like a spring that absorbs any change in the demand without affecting the price match. But in Bitcoin, adding more miners doesn't increase the supply of block space at all. Blocks will continue to be created every 10 minutes on average. Hence, the supply is completely inelastic, and any seasonal change in demand is fully reflected in the price. It is worth pointing out that while having more miners doesn't increase the block space, it does improve the network security. Many recent technologies in blockchain, like rollups and parachains, answer the question of how to scale up the block space without affecting security. The goal is to make block space more elastic, so it can better match the demand. Another scarce resource in blockchain networks is state storage. Another scarce resource in blockchain networks is state storage. This time, let's take Ethereum blockchain as an example. It is run by computers around the world called validators, equivalent to the role of miners in Bitcoin. Ethereum allows developers to deploy applications called smart contracts, which makes the network incredibly versatile. But unlike transactions that occupy a single block, the data generated by smart contracts needs to be stored permanently by all validators. The aggregate of all these application data constitutes Ethereum state, and it is currently hundreds of gigabytes in size and growing. The problem is that much of this state is all data that no one uses anymore. This is known as the state bloat problem. Evidently, there needs to be incentives in place to stop this resource from being wasted. One way to solve this is by introducing state rent. The idea is simple. Users pay rent for the storage space their contract occupies. If they stop paying, their data gets evicted. This encourages developers to be more mindful about the space they're using. Ethereum, on the other hand, does something slightly different. Developers provide a deposit in Ether when they deploy a smart contract, and receive a refund when they clean up data they no longer need. Speaking of incentives, this brings us to opportunity cost. Let's say you've deployed a smart contract and paid the storage deposit for it. If you come back a year later and get your deposit back, can you say that storage was free? Not really, because you paid an opportunity cost. The tokens that were locked as deposit could have been staked or could have been invested elsewhere. So this incentive model ends up being similar to state rent. Opportunity costs are often overlooked by people, possibly because they are difficult to assign a value to. In 2019, in a period where it was common for new blockchain projects to airdrop their tokens as an initial token distribution, the project Edgeware used a new concept called a lock drop. Instead of making participants buy tokens, they just had to lock up their Ether for a period of time, and they received a proportional amount of Edgeware tokens. This is an interesting experiment because it linked its initial market value precisely to people's perceived opportunity costs of locking Ether. Alright, let's move on to network effects, which is another key concept in blockchain economics. A network effect happens when the value that a user derives from a service depends on the number of other users of that service. We see this in telephone networks, social media apps, financial exchanges, and also in blockchain. Private companies can typically use network effects to gain a competitive advantage. This is why, for instance, it is difficult to create a new social network app. You can have better functionalities than the main networks, but people will not like it very much because they have no one to interact with. The case of blockchains like Ethereum or Polkadot is different because they are public infrastructure, so the network effects benefit everyone. Unlike a traditional network in Web2, where every application belongs to a single company, applications in Ethereum or Polkadot can be created by anyone. So users, developers, and validators take advantage of the network effect, which creates more interactions and business opportunities and increases the token value. To summarize this lecture, we talked about markets, especially the volatile Bitcoin fee market, and how newer blockchain technologies are trying to make block space behave more like a traditional commodity. We've also seen how state storage works in Ethereum and how opportunity cost plays a role in blockchain systems. And we saw the network effects drive up the value of major blockchains. These are just a few examples of how economic concepts help us better understand the current landscape in blockchain and prepare us to make valuable contributions to it.
think in economics we have different perspectives. Ones are like purely theoretical ones that very like assuming high rationality in agents, right? And then there's the other aspect where economics is actually working together with psychology. And this is, I think, a very interesting section because I also did my PhD in there. And it is, I think, much more informative when you think about real world applications and actual interactions between humans, because they often don't really act rational, but they are also not random, right? They don't do random things. They just often are not behaving as you would expect them to behave from traditional economic concepts. So I think it's quite interesting to actually combine psychology with economics, which is the field of behavioral economics. And yeah, this is the field that I also did my PhD in. I think one of the most important parts in when you design blockchains is that you try to do it permissionless and open for everybody. And there you don't have access to many of the social mechanisms to enforce certain behavior, right? So you often don't know who are the actors. And that means that you need to drive their behavior with economic incentives. You can both like understand economics and then learn about protocols that are out there, or you can learn economics and actually design various mechanisms and protocols, right? So I think it's knowing about economics can bring you benefits on both sides, whether you're like an active developer or whether you're just like part of the system. A Schelling point is actually also very interesting because it introduces, again, psychology to the mix. And basically, a Schelling point is some kind of situation, an outcome or something, or a choice that is in some form intriguing to humans. So on a purely mathematical level, there's like no indication of why that is an interesting point. But a Schelling point is recognized by many humans to be a nice outcome or a nice choice. For example, if I would ask you, let's say you are in prison and another person is in prison, and you would ask them to guess a number, and only if all the people would guess the same number, they would be released. And now the numbers that you can guess from is 0.37, 1, and 1.65 or something. Right? And only if both people guess the same number, they get out of prison. The likelihood that both people would say 1 is like super big, right? Because it's a nice number, it looks nice, and it's kind of relatable to everyone. So actually the probability to be released is much higher than, you know, like the combinatorial thing of like guessing the same number. And that is a Schelling point, right? Like the 1 would be a Schelling point. So the tragedy of the commons is a very common concept that we see everywhere also in daily life, where basically people are benefiting from something, but it takes effort to create it or money to create it, and it cannot be really attributed to who is like contributing to it, or even more importantly, who's like able to consume it, right? So in short, it would be nice if everybody would contribute to something, then we could all have a nice thing, but everybody else is kind of better off to save their own resources and let other people contribute to something, right? So you're kind of the free rider. You would hope that other people create something nice and you just benefit from it. And since everybody is kind of in that situation, it can happen that this nice thing is never getting funded or like produced because there's not enough resources of people that actually contribute to this. In the field of blockchain, it's very interesting because we can program in rules on the protocol level to solve this issue. For example, on Polkadot, we have the treasury, which will receive a fixed inflow from the inflation. And from this, then projects can be funded that probably wouldn't be funded individually, right? Because it will benefit all the token holders and it induces costs on all the token holders. And this is kind of solving the tragedy of the commons, at least in that regard.
Welcome to the Blockchain module, the gateway to mastering blockchain technology and becoming a Web3 developer. This
History of money and trust. Money has been a central aspect of human history for several thousand years, and it still continues to be. Money permeates almost every aspect of our modern life, and it is surprising to see how little we are aware of how it is created. How is money created? It is a question everyone should be asking. If you're wondering why this question is relevant for a technical course on blockchain, you should be looking at the Genesis block of Bitcoin network and a code that was embedded in it pertaining to banks. If you look around yourself, you see that debt is an integral part of individual lives and institutions. Almost every country in the world has a national debt, which only keeps growing each year. Who do they owe that money to? How did that money come into existence? Can banks legally loan more money than what they have in reserve? What causes hyperinflation and devaluation of currency? A few interesting questions to ponder, right? We all place immense trust in centralized institutions and hope that they act in our best interest. But history shows us that such trust can be taken advantage of.
Humans have coexisted through various social mechanisms for hundreds of thousands of years. Our ancestors started as hunter-gatherers and discovered farming and domesticated animals for food and service. Then they progressed to complex societies, which marked the beginnings of the modern nation-state. Social hierarchies became more complex, leading to our current state of affairs. Over this long period, we've continually worked on better ways to understand and coordinate with each other. From performing incredible feats like flying into space, building skyscrapers, or winning sports tournaments, to following simple rules to avoid collisions on the road by driving on the opposite side. Coordination plays a very important role in our day-to-day lives. Both of these forms of coordination are valuable. As our population grows, our ability to coordinate becomes even more crucial. This need has always existed, and today I argue that blockchain represents our generation's contribution to this ongoing project of human coordination, one that stretches all the way back to the dawn of our species. Throughout this course, we'll explore blockchain from philosophical and technical perspectives. By the end, we'll understand it as a tool for coordinating with people we don't necessarily trust. Think about it. While you trust your close friends or family, most people you meet on the street are strangers. Yet, society depends on us all following shared rules, whether it's driving on the correct side of the road or engaging in business deals. So what does blockchain add to the equation? Well, it allows us to bring the same kind of mathematical guarantees that cryptography offers to a wide range of digital services. Cryptography guarantees the privacy and authenticity of messages, even if someone's listening in. Blockchain does the same for institutions and services we rely on, such as vehicle registration, business transactions, or even voting systems. In a way, blockchains commoditize trust and let the code be law. Take the Bureau of Motor Vehicles, or BMV, in the USA. On the surface, it's a boring institution, but it's essential in ensuring that vehicles are safe and people can legally drive. BMV, like any other organization, is not infallible and can make mistakes. Now imagine if we could remove the potential for human error or corruption at the BMV and replace it with cryptographic guarantees. If you register your car, you'd have full assurance that your registration can't get lost within the system. That's what blockchain does. It builds trust through technology, not through the need for human intermediaries. But there's more to the story. Blockchain helps us agree on shared histories, shared stories, if you will. A shared story or history is crucial to establishing trust. This has always been true, whether we're talking about ancient societies or modern institutions. Every large-scale society, whether it's a modern government or a medieval church, relies on shared stories that exist in our collective memory and imagination. These stories are powerful tools for convincing people to cooperate and align their goals. So why are shared stories important? Think about it. When I meet someone on the street, it's a low-trust situation. But if I know we share certain beliefs or cultural background, it becomes easier to cooperate. This idea of shared stories applies to everything from ancient creation myths to modern legal structures like limited liability companies. Just like ancient societies rallied around their shared myths, today's societies rely on stories too, though they may be about things like corporate structures or government regulations. Take the Bitcoin blockchain as an example. The text embedded in Bitcoin's Genesis block refers to a newspaper headline about the global financial crisis. It serves as a rallying point for those who believe in Bitcoin's principles of sound money and financial fairness. In a way, it's a modern creation myth, bringing together people who share a vision for a more decentralized and transparent financial system.
Buckminster Fuller. He was a great guy. He had a lot of interesting and insightful quotes, and I'm going to start the talk with one of them. Here he's pointing out that if you actually want to change things, then it's no good fighting, right? That doesn't lead to anything. In fact, the way to change things is to create something new that obsoletes the existing order. So I want to explore what the existing order is, because unless we know that, it's going to be difficult to understand how it can change. Here's a few pictures of some buildings, places. Does anyone know, can anyone identify any of these? Feel free to shout out. New York Stock Exchange? Yep, that's right. Say again? Monte Carlo, indeed, yep. Okay, so the UK Land Registry is the top right. PayPal's headquarters, top middle. And actually, the bottom right isn't quite the existing order. The bottom right is the now defunct Lehman Brothers Bank. What do they all have in common? Institutions, right? They do things, they sit at the center of society. They manage people's business. They manage people's assets. They manage people's transactions. But I want to look a bit deeper. I want to understand better what these all have in common. In fact, they operate in a pretty similar way. They all have very specific operational building blocks. They begin by accepting instructions from their clients or from the external world. Really, these are just messages. They're messages that are authenticated in some way. For example, a bank might authenticate a message by virtue of seeing me in person sign an order. Maybe it was a phone call. A casino might authenticate a message by simply having a croupier that sees that I am placing a bet with my chips on the table by moving them onto a particular portion. The other two things are, in fact, computation and record storage. So different institutions manage their computation and record storage in different ways. A bank, of course, has lots of records of people's account balances, and the computation is relatively simple. It's addition and subtraction, by and large, with some multiplication for managing interest rates. Casino might have a little bit more multiplication in there, but very similar activities. Now, if we break it down in this way, we find we don't quite get what it is to be one of these institutions. There's something missing. This is what we would call a computer in the 1940s. It's really the inner workings of an institution. It's a lot of people who are processing information. They're doing arithmetic. There are some records at the back. You can see it in the back of the picture, some drawers, where they will get up and go to in order to store or retrieve some information. And there will be instructions coming in periodically from the mathematicians that actually want those computations to be done. But this misses the point. In fact, the institution cannot simply be boiled down into these three things with a large building around them. Institutions deal with contention. They have to deal with contention because they are managing economically important data. The Land Registry Office manages the information that determines whether I own some property or I do not. Banks have numbers in them. The numbers are not meaningless numbers. They determine the difference between rich and poor. They manage contention by virtue of having this fourth attribute. In addition to the three attributes of operation, they have authority. And it's with this authority that they can determine, that they can give semantics to these numbers, to this data. It's authority, which is the difference between the land registry being a shopping list of property that I would like to own, and the difference between owning a house and not. We can then build a better model of what it means to be an institution. An institution is this information processing, but it's backed up with authority. Some institutions, like, for example, aspects of the government, their authority is actually the military, right? The police force, the security forces. Others rely on the government in order to exert their authority by virtue of civil law, such as PayPal, the banks, and so forth. And this is a pretty good model of what it actually is to be an institution, and therefore a pretty good model of how society works, economically speaking, in its innards. We can model the way that society works as being a bunch of these institutions, each, of course, with their own cartman, their own authority. And this is pretty much how society has worked for centuries now. Of course, in the meantime, there have been improvements to how we can determine whether a message is authenticated. Instead of using telephone calls or signatures, we increasingly use things like elliptic curve cryptography, a branch of mathematics that allows us to know whether someone purporting to be a particular identity is actually that identity without giving any of the information that could allow others to claim the same thing away. Instead of storing things in books, we store things instead on magnetic media or increasingly little microchips, solid-state media. And rather than using abacuses or handwriting arithmetic, we use, of course, silicon. We end up with computers. Unfortunately, while within an institution, the computers can allow things to go much faster than they would otherwise have been going. Between institutions and across trust boundaries, they're of no use. In fact, the world is much like a set of walled gardens. Within the garden, you are free to play. You accept the authority of the household that actually owns the garden, but it's very difficult to get between the gardens. In reality, this boils down to banks and various financial institutions having a very difficult time consolidating transactions that go between them. But the more important thing is that as individuals and small business owners, it's very difficult for us to interact with each other if we don't yet know or trust each other. Instead, we have to go to these guardians of society, these intermediaries, these trusted authorities, the middlemen, in order to interact. And this comes down, we can see this every day. If I want to interact with my friends, I go to a website. The website is called Facebook.com. I go and contact Mark Zuckerberg's company in order to pass on a message to tell my friends, hey, maybe we should go out. This is not quite the way the world was meant to be. I should not need to contact Mark Zuckerberg in order to actually say hello to my friends. There is a new technology, which was mentioned just before I came on stage, which changes things, which obsoletes this old order. This is my artistic rendition of this new technology. Atop the picture reads A pluribus unum, from the many, one. And what the technology allows us to do is to come together, globally speaking, and form a consensus. Form a single opinion on what happened, and when it happened, and what should happen because of it. Effectively, to form a single institution. Now, the institution will operate correctly down to the rules of mathematics and economics that this system works on. In effect, everybody can ensure that the system as a whole is operating correctly from their own point of view. Everybody has the freedom to check. In that sense, blockchain has solved this issue of multi-party contention. And it's done so without having to have redress to a human organization. We don't anymore need to trust, strictly speaking, in order to interact economically with somebody that we do not know. And that's the first time that we've been able to do that in society, which means, practically speaking, we've just commoditized this crazy asset, probably the most expensive asset to hold of all, trust. And I put it to you that in the future, trusting an opaque institution, a middleman, merchant, or intermediary with our interests will be as archaic a concept as reckoning on our is today. Thank you.
Let's now take a look at the evolution of technologies that humans have used to coordinate and tell these stories. In the beginning, we relied on oral traditions, stories passed from one person to another. But as these stories evolved through word of mouth, inaccuracies crept in, much like a game of telephone. Writing eventually emerged, allowing us to document stories more precisely. From hieroglyphics to the phonetic alphabet, we moved from oral tradition to written records. Then we got the printing press. Suddenly, information could be mass-produced, enabling wider access to knowledge and more efficient coordination. The printing press was a leap from centralized systems of control like scribes and governors towards a more decentralized spread of ideas. The internet, in many ways, is the next step in this evolution. Today, we're in the era of Web 3. Web 0, predating the internet, relied on peer-to-peer communication through technologies like the telephone or the telegraph. Web 1 was the early internet, where static data was shared between servers and users. Web 2 brought us dynamic digital services, things like MySpace or Gmail, where content evolved through user interaction. But there's a catch with Web 2. In this era, we're required to trust the service providers with our data. Whether it's MySpace, Facebook, or the Bureau of Motor Vehicles, we're relying on intermediaries to maintain the integrity of the services we use. And as we've seen, these intermediaries can fail or even at times act against our interests. This brings us to Web 3, where blockchain enables trustless infrastructure. We no longer have to rely on service providers to maintain the integrity of our data or services. Blockchain, through its consensus mechanisms, ensures that services run as expected, even if some participants try to cheat the system. Game theory and cryptoeconomics underpin this trustless system, making sure that even decentralized operators are incentivized to act honestly. In Web 3, anyone can access these services without fear of being censored or excluded based on arbitrary metrics. The system is decentralized, and the rules are baked into the infrastructure itself. This leads to greater privacy, authenticity, finality, and importantly, unstoppability. Finally, let's talk about why all this matters. In a world where digital services are increasingly important, we want strong guarantees that the services we rely on will work as expected. Blockchain allows us to provision services that are immune to censorship, tampering, or failure by intermediaries. The service is provided by a decentralized network that's economically incentivized to behave fairly. So, that's a big picture of what blockchain brings to the table. It's not just a new way to manage money, it's a tool for human coordination on a scale we've never seen before. Through cryptographic guarantees and decentralized consensus, we're building the infrastructure for a future where trust is built into the very fabric of our system. And that, in my view, is our generation's contribution to the long human journey of figuring out how to work together. Let's now take a look at the evolution of technologies that humans have used to coordinate and tell these stories. In the beginning, we relied on oral traditions, stories passed from one person to another. But as these stories evolved through word of mouth, inaccuracies crept in, much like a game of telephone. Writing eventually emerged, allowing us to document stories more precisely. From hieroglyphics to the phonetic alphabet, we moved from oral tradition to written records. Then we got the printing press. Suddenly, information could be mass-produced, enabling wider access to knowledge and more efficient coordination. The printing press was a leap from centralized systems of control like scribes and governors towards a more decentralized spread of ideas. The internet, in many ways, is the next step in this evolution. Today, we're in the era of Web 3. Web 0, predating the internet, relied on peer-to-peer communication through technologies like the telephone or the telegraph. Web 1 was the early internet, where static data was shared between servers and users. Web 2 brought us dynamic digital services, things like MySpace or Gmail, where content evolved through user interaction. But there's a catch with Web 2. In this era, we're required to trust the service providers with our data. Whether it's MySpace, Facebook, or the Bureau of Motor Vehicles, we're relying on intermediaries to maintain the integrity of the services we use. And as we've seen, these intermediaries can fail or even at times act against our interests. This brings us to Web 3, where blockchain enables trustless infrastructure. We no longer have to rely on service providers to maintain the integrity of our data or services. Blockchain, through its consensus mechanisms, ensures that services run as expected, even if some participants try to cheat the system. Game theory and cryptoeconomics underpin this trustless system, making sure that even decentralized operators are incentivized to act honestly. In Web 3, anyone can access these services without fear of being censored or excluded based on arbitrary metrics. The system is decentralized, and the rules are baked into the infrastructure itself. This leads to greater privacy, authenticity, finality, and importantly, unstoppability. Finally, let's talk about why all this matters. In a world where digital services are increasingly important, we want strong guarantees that the services we rely on will work as expected. Blockchain allows us to provision services that are immune to censorship, tampering, or failure by intermediaries. The service is provided by a decentralized network that's economically incentivized to behave fairly. So, that's a big picture of what blockchain brings to the table. It's not just a new way to manage money, it's a tool for human coordination on a scale we've never seen before. Through cryptographic guarantees and decentralized consensus, we're building the infrastructure for a future where trust is built into the very fabric of our system. And that, in my view, is our generation's contribution to the long human journey of figuring out how to work together. Let's begin with the core goals of blockchain systems. First, we want trustless infrastructure. This means eliminating the need for centralized server operators who often compromise our privacy. Second, blockchains are tools for coordinating with people globally, people you may not know or trust, but need to interact with for trade, projects, or even voting without relying on an intermediary. Blockchain systems build trust through cryptography. Just like how cryptography provides guarantees in messaging, when you send an encrypted message, you're assured of integrity, non-repudiation, and authenticity. Blockchains apply these same guarantees to whole systems, not just messages. Before we dive into Web 3, let's take a quick tour through the evolution of the web. I like to call the earliest form Web 0. Web 0 refers to the time before the internet, with technologies like telegraphs and telephones. These relied on physical wires and human operators with little to no cryptography unless you were in the military. But even then, Web 0 was an ideal use case for cryptography. Web 1 came next, introducing always-on servers. For instance, a scientist might want to publish a paper on their server, and others could access it at any time. This was mostly peer-to-peer, but cryptography was still underused because the threat models were not well understood. Then came Web 2, and this is where things really changed. Web 2 introduced applications like social media platforms or government services, such as renewing your vehicle registration online. But with this, we lost the peer-to-peer nature of Web 1. Instead, everything was centralized around service providers. Facebook, for instance, controls what posts we see, and we can't verify whether they're altering the information. Even if you see that reassuring HTTPS lock symbol in your browser, it only guarantees secure communication between you and Facebook, not between you and other users. This centralization creates opportunities for censorship, manipulation, and failure where users are left trusting intermediaries who could change the terms at any time. In Web 2, service providers often abuse their control. They can censor content, block interactions, or simply fail to provide requested data. More alarmingly, they can modify the data behind the scenes, and you'd have little or no control over it. This is where blockchain steps in. The first blockchain most of us heard about is Bitcoin. Bitcoin introduced a new concept, a shared ledger with immutability. It wasn't just a digital currency, it was a new way to track a shared history, ensuring no one could tamper with past transactions. While Bitcoin pioneered the concept, Web 3 takes it further. In Web 3, we provision digital services without needing to trust a service provider. Instead, we use economic and game theory tools to incentivize service providers to behave honestly. It's no longer about hoping the service provider stays benevolent. It's about aligning incentives so they are rewarded for honesty. So what do we want from Web 3 systems? First, permissionless access. Anyone should be able to use these systems regardless of status or location. We want also privacy. Users should control what information is shared and with whom.
Authenticity is crucial, ensuring we know who sent messages or transactions. And then there's finality. When a transaction is completed, like registering a vehicle, we want to know it can't be arbitrarily undone. Blockchain solves many of these problems by allowing all users to agree on a shared history. Much of human coordination revolves around shared myths or stories. Blockchain is the next step in that evolution, enabling large-scale coordination through a shared immutable history. Now, let's talk about how blockchains evolved. Bitcoin introduced the concept of an immutable ledger using a model called UTXO, which tracks unspent transactions. Soon after, people realized they could tweak Bitcoin's code to create new cryptocurrencies like Litecoin, Monero, or even Dogecoin, each with slight variations but using the same basic principles. The real breakthrough came with Ethereum. Ethereum took the idea of a shared ledger and added a Turing-complete state machine, which allows for more complex applications beyond just currency. With Ethereum, you can build anything from financial systems to social media platforms on top of a decentralized blockchain. Ethereum introduced the concept of smart contracts, where each contract can have its own internal state, managed by the Ethereum virtual machine, EVM. This opened the door to an array of new blockchain applications, many of which aim to improve on Ethereum by enhancing scalability, interoperability, or consensus mechanisms. With the mass adoption of Ethereum, the blockchain trilemma came to the limelight. This trilemma states that it is inherently challenging to achieve three key aspects of blockchain technology simultaneously: security, scalability, and decentralization. For instance, Ethereum is fairly secure and decentralized, but has issues with scalability. This is why you can see numerous blockchains serving as rollups on Ethereum to improve its scalability. After Ethereum came networks like Polkadot and Cosmos, which envisioned an interoperable multi-chain future for Web3. Monolithic blockchains like Solana prioritized scalability and performance. These are exciting times, with a lot of innovation happening to create multi-chain solutions to maximize security, scalability, and decentralization. In summary, blockchains have evolved from Bitcoin's simple ledger to Ethereum's rich, decentralized applications. Web3 is our next step in building trustless systems that empower users, removing the need to trust intermediaries. By combining cryptographic guarantees, consensus mechanisms, and shared histories, blockchains offer a transparent and secure future for digital services.
Ideal Web3 application properties. The first one is that a Web3 application should be unstoppable. When we develop and deploy a Web3 application, we should be assured that no single entity can unilaterally stop it. A lot of blockchain networks have the emphasis on liveness, and hence the application powered by a decentralized live blockchain will have this particular property. Web3 applications should also be seamlessly upgradable. It would be highly impractical to imagine internet applications if there was no room for updates, right? There are blockchain networks that support seamless upgrades and updates, and it is worth checking them out. Web3 applications should also be unlimited. The ideal property of limitlessness here highlights the elastic property of Web3 applications. The underlying technology stack should scale based on the demand that is out there. The next property is high on my wish list for using Web3 applications, that it should be feeless. Do not be misled with this property here, as there is always some cost involved, and a Web3 application should always have a revenue model to sustain its existence. An ideal Web3 application will be feeless or will have a predictable fee model. This ties very well into the advent of tokenized networks that are predominantly present in Web3 space right now. Web 1, the birth of the internet itself, was a revolution. It enabled an information economy that thrived on making information available for everyone. Then we have Web 2, which was a result of the front-end revolution that has let anyone create content and post on it. This enabled platform economy where all they had to do was focus on creating a platform that is used by the content creators, and they figured ways to monetize this content and its users. While this is a tried and tested business model, this also created single points of failure and significant centralization. It also enabled the middlemen to take a huge cut from the rewards earned by the content creators. This led to where we are today, with the revolution happening in the backend, which directly works towards eliminating the central entities. Web3 not only enables you to own your content, it also enables you to execute a set of functionalities which were gated by the central authorities in Web 2. This is enabled through tokens. For instance, Ether, which is the native token of Ethereum, can be used to execute smart contracts deployed on Ethereum network. A typical Web 2 application requires you to set up your account through entering some level of personal information, which is stored on their servers that are either administered by them or a third party. Your access to that application can be partially or fully restricted or revoked by the application provider. It typically follows a client-server architecture, and it is possible that the application provider uses a lot of redundancy at the back end, but you keep hearing about the outages that happen to the applications administered by the tech giants, right? So it's quite common. This happens because of the single point of failures that are imminent in central entities. On the other hand, a Web3 application typically requires what is called a wallet, which is based on an account that has a private key. It is also possible to use the same wallet across multiple Web3 applications. This wallet account is pseudonymous on public decentralized blockchain networks, as the account activity is visible publicly, but Web3 also offers privacy solutions on public blockchains. You can share your identity with the applications that you trust. The network follows a peer-to-peer decentralized architecture, and hence the network is immune to single points of failures. Challenges of Web3. I need to emphasize that Web3 is just getting started, and there is still a lot of challenges we need to overcome to have a mass adoption. The first one is the accessibility aspect of Web3. How accessible are Web3 applications today? We say Web3 applications are trustless, but what hardware and software do we need to trustlessly interact with the Web3 applications? The next one is very critical. It's the user experience, right? How easy is it to deal with wallet accounts? What happens if you lose your private key for that account? What happens if your key was stolen? What are the things you need to be aware of before you use Web3 applications? Are we all educated about the benefits and the potential risks associated with them? And that brings us to the final challenge, which is attaining an acceptable level of decentralization. Again, this is a hot topic which is always up for debate, but you now understand that true decentralization is actually a spectrum, and it mainly ensures that a single entity cannot unilaterally exert control over the entire network. I hope this module gave you an overview of how blockchain technology fits into the everyday applications that we use on the internet.